This lesson is for FST, lesson 11.4 on the central limit theorem. We'll explain more about what the actual central limit theorem is and why it's named that later on in the video. First, I want to do a little bit of reading from our textbook. The textbook does a fairly decent job in chapter 11 of explaining things, so rather than me trying to summarize on my own, I think the book's words here are beneficial. So we're going to start with page 706. It's often too costly, too difficult, or simply just impossible to study an entire population. For these reasons, usually a sample is taken and inferences are made about the population and the sample data. However, characteristics of the sample are not likely to be identical to the characteristics of the population, even if that sample has been randomly selected or even carefully selected to be representative of that population. For instance, the means of various random samples from the same population are likely to differ somewhat from each other and from the population mean. So, to understand how measures of a sample are related to the corresponding measures of the population from which it was taken, it's helpful to study how different samples drawn randomly from that same population will vary, and to study the distribution of sample means. So moving forward, there's some symbols that we need to make sure students are comfortable with. When the textbook refers to SRS, they're talking about a simple random sample. So it's simply an abbreviation that they're using there. It's not really anything that you need to worry about, but just be able to recognize it when you see it. A reminder here that the mu symbol stands for mean of a random variable. When we modify that symbol to have a subscript with an x bar in it, now we're talking about the mean of the sample of that random variable. And then similarly for the standard deviation, when there's a subscript x bar with it, you're going to call that the standard deviation of a sample. And we'll talk more about those symbols here in just a moment. So now let's actually look at the central limit theorem itself. Often abbreviated CLT, it's located on page 710 in your book. If you suppose that all random samples of size n, so that's the size of the sample, are selected from a population with a mean mu, standard deviation of lowercase sigma, then as n increases the size of the sample, the distribution of the sample means will approach a normal distribution with the same mean, and the standard deviation will approximate or approach the standard deviation divided by the square root of the sample size. Notice that the means are going to be the same when the distribution is normal. The standard deviation will be smaller than the original because it's getting divided by the square root of the sample size. Now let's look at why it's called that. Central limit theorem is central because it deals with the mean, which is a measure of center. It's also a limit theorem because it deals with what you can expect as the n increases for larger and larger sizes. So think about that for a moment. As the sample size increases, the standard deviation will decrease. So that's an inverse operation. That's an important idea to keep in mind. As the sample size grows, the spread of the data will not, because you have more samples to go by. The importance of the central limit theorem is that it applies widely to lots of different situations. Even if the underlying population distribution is not normal, the central limit theorem states that the means of samples of a sufficient size will be normal. So what do they mean by sufficient size? The theorem itself doesn't specify, but over the years there has been a rule of thumb that has been determined. And so that's our other thing that we need to talk about today, and it's the central limit theorem corollary. A corollary is just an offshoot of a theorem. So if you consider a population where you take random samples of size n, the distribution of sample means will be approximately normal when one of the next two things happens. Either the population itself was stated to be normal, or the sample size is 30 or greater. So the sufficient size is now that number, 30 or greater. Now, if you get both of these things happening at the same time, then that's just a bonus for you. Then you know for sure that you can calculate the mean and the standard deviation of the sample. But if you only get one or the other, that's fine too. So let's try this out in an example. A manufacturer claims that its fluorescent light bulbs have a mean life of 2,000 hours with a standard deviation of 300 hours. A lab purchases 64 bulbs in order to test their claim. What is the shape, mean, and standard deviation for the sampling distribution of the mean for sample size of 64? So first we need to verify, does it say that the distribution of light bulbs is normal? Definitely not. It doesn't say that anywhere in there. Also, when they ask you for the shape, they're asking you, is it normal or not? That's another way of them asking it. So we don't know if it's normal for sure just by what they've told us, but we also know the sample size is greater than 30, so that's good enough. So the shape is going to be normal. So that part's done. The mean, since it is normal and the sample size is sufficient, the mean of the original and the mean of the sample are going to be the same. So in this case, let's find it. The mean was 2000. Standard deviation of the sample is going to be, do you remember the new formula? The original standard deviation divided by the square root of the sample size. So the standard deviation was 300 and the sample size was 64, so we're going to divide by square root of 64. So when you type it in on your calculator, you're simply going to type in 300 divided by 8, I hope, so that'll save you a little bit of time. So you should get about 37.5.